And then probably somebody will put it on YouTube at some point. Okay. So let me introduce you, Francis. So welcome everyone to this first MIPP seminar of the academic year. And Francis Bloch is a professor from Paris School of Economics. He works mostly on matching and networks, but he has important papers about many topics, and he was very generous to give us a seminar. Now this one is on networks. So Francis, thanks again, and the floor is yours.
Thank you. Thanks, Rami. So thank you all for attending. It's actually not too bad to speak in Chile because the time difference is okay. So I'm very happy to be with you here. I would love, of course, to be with you for real. So the paper I'm going to be presenting is a paper on networks, and it's joint work with Kalyan Chatterjee and Bhaskar Datta, and it belongs more generally to a recent area of study of attack and defense in networks. So it's actually a paper which is easy to motivate. If I manage to move to the next slide. So in the end, what this is going to be, it's going to be the model of a game between an attacker, and the attacker sends an object to some node in the network, and each of the node is going to be a defender, and the defenders are going to try to intercept or to stop the object. So if I say that, you can think that actually there are zillions of papers looking at this. So you would be partly right. I mean, there's a huge literature that I'm going to be talking about, particularly in operations research, where people have looked at problems of interception in networks. But I'm also going to argue that the particular game that we look at is something that has not been looked at before, and it's a game which is probably going to be quite interesting. So as I said, I mean, I don't think there's many, it's too difficult to motivate what we're doing here. So what really we had in mind was the idea of a terrorist sending a bomb or possibly a biological agent or a virus through a network. And the attacker then would be the terrorist. And then in red, you see who the defenders would be. The defender would be counterterrorism agents or airport security agents. Now, the list can go on and on. I mean, you can think about drug lords sending packages of drugs through a transportation network, and the people trying to stop them would be local police officers. You can think about hackers sending a virus or malware in a network of computers. And some people actually have looked at one particular example where people are sending nuclear material through a transportation network, and the objective is to try to stop that nuclear material from emerging. So there's clearly a lot of situations which look like that, where somebody is using a network to move an object in order to attack a particular target, and people are trying to prevent to intercept the object. So it actually turns out that this is a running example that I'm going to be using throughout the talk. So it's supposed to be a hypothetical story of a terrorist living in Baghdad, whose objective is basically to drop a bomb somewhere in a place where it would be, where it would make a lot of noise. So what you see here in front of you is the actual network of flights, of current scheduled flights that you can take if you were to go from Baghdad to a city, either Paris or London or New York City. So what I did, basically, I used the website to check which flights are leaving out of Baghdad. And out of Baghdad, actually, I use Baghdad because there are very few flights out of Baghdad. So it's easy to construct the network. Out of Baghdad, there are only 4 destinations that you can go to, which are Istanbul, that's for Rami, Beirut, Amman, and Dubai. And from there, if the question is basically, how do you go from there either to London or Paris or to New York. And what I showed you are, I mean, there are many, many ways in which you can go from Dubai to New York, but I looked at the most direct connections from Dubai or Istanbul to go to London and Paris. And as you see, for example, from Amman, Amman is a relatively small airport, so it has flights to London, but it doesn't have direct flights to Paris or New York, for example. And Beirut has flights to Paris and London, but not direct flights to New York, etc. Okay, so the question, that's the question that we're asking. We're saying, suppose that you're a terrorist, you live in Baghdad, and where are you going to drop the bomb? So this is one part of the data that we're going to be using, which is the transportation network. The second part of the data, and this is of course much more subjective, is what is the value for a terrorist of attacking the different targets. And it's very subjective. So basically here, I'm drawing something which is completely out of my hat, and it may be completely crazy, but but we could redo the analysis and check the robustness by changing those numbers. But what those numbers are supposed to represent is the value of a target for a terrorist. And what we did actually is very simple. We divided the set of cities into three different types of cities: cities in the Middle East, cities in Europe, and cities in the US, and assumed that actually the target had higher value in New York than London and Paris, higher value in London and Paris than in all four cities in the Middle East, and then gave numbers that a little bit completely subjectively. But I want you to think about these as the two data that we're going to be using: values of the targets and the transportation network. And that's all the data that we have. And the question we're asking then is, what is the equilibrium? Where is the terrorist going to attack? What eventually are going to be the probabilities with which he's going to be attacking the different cities? Because you're going to see that most of the time the equilibrium is going to be an equilibrium in mixed strategies. So the terrorist is going to choose probabilities of attacking the different targets, and which are the paths which are going to be used to go, for example, from Baghdad to New York. So as I told you, I mean, we're definitely not the first people to think along those lines. And there's a literature, and I'll give you some references in a few slides, particularly in operations research, and that problem is called network interdiction. So network interdiction originated in the 1960s, really as a problem, military problem. And people looked at three different versions of the problem. The first version is called shortest path interdiction. And here, the question you're asking is basically, what are the arcs, the edges in the network that you need to take away in such a way as to make the shortest path between two nodes, called the source and the sink, as long as possible? Okay, so the question is basically, if you were to bar, so here think about troops moving from point A to point B. And the question is basically, if I could remove some edges or bar some roads, which one should I do it in such a way as to make the path from A to B, the shortest path, as long as possible? Second type of problems that people have looked at, more linked to drug trafficking, is basically, suppose that you have a network with capacities, and each link has a given capacity, and the objective of the attacker is going to be to move drugs from point A to point B using the capacities in the network, and the police is going to try to basically, it can change the capacities in the network, and it will try to do it in such a way as to minimize the flow going from A to B. And finally, there's the so-called problem of reliable path interdiction, which is closer to what we're doing, where the question is basically the police is putting detection devices on the different paths, and it wants to do it in such a way as to detect with the highest possible probability a movement from point A to point B. Now, notice one thing, that every time there's a network interdiction problem, there is a given point A and a given point B. There's a source and there's a sink. So the problem is to select a path from the attacker, but it's not to select a target. And that is pretty much what we're adding to the literature. We're basically allowing for the endogenous choice of the target. And which one is the good model, I think depends on the application. So if you think about troop movements, it's probably the source and the sink are given. But if you think about drug trafficking, or if you think about terrorist attacks, I think there you can argue that the destination point is also part of the endogenous choice of the attacker. And that, of course, the attacker is going to choose a destination point in order to fool the police or to fool the defenders. So that's exactly what we want to study here. It's basically that endogenous choice of targets and the probability distribution over targets as a way to prevent the defenders from defending. Okay, so what's new in this paper is first that we look at a full-blown game theoretic model. So we're going to be computing equilibrium, which is typically not what is being done in operations research, where people are more interested, maybe for good reason, in computational problems. So how complicated is it to compute to a particular linear programming problem, etc. The second big difference is that we're going to consider a decentralized model. So each node is going to be its own defender. And if I have time towards the end, I can tell you a word about what's happening if we allow nodes to coordinate in defense. And finally, that endogenous choice of targets and the fact that targets have different values, that's completely new to the literature. Okay, and the questions that we're going to be asking and hopefully answering are these ones. I mean, first, the real surprising result of the paper is one which says that actually the Nash equilibrium of the game that I'm going to be describing in a few moments, but it's a very natural game, that it has a unique Nash equilibrium. And that's actually quite surprising to us. So that's the only really challenging result of the paper. So that's the first part, is going to be studying the Nash equilibrium of that game and showing that that Nash equilibrium is unique, and characterizing the Nash equilibrium, telling you how you can compute the equilibrium attack paths. And in the end, out of my network going from Baghdad to London, I'll give you the precise answer to tell you exactly which cities are going to be attacked with which probability and through which path. The second part of the paper is going to be doing some comparative statics. And as I argued before, it's a very sparse model, because the only information we have is the network and the target values. And that's the only thing that we can change. And that's what we will change. We will look at what's happening when you change the architecture of the network, typically when you add or delete links. And you will see that there's something a little bit surprising here. And also, we're going to look at what happens when you change the value of the nodes, when some nodes have higher or lower values. Then, at the end of that, we're going to be looking at two, initially we call them variants of the model, but now given the current circumstances, we call them variations rather than variants. So we're going to be looking at two alternative models, one in which nodes are going to be inspecting conditional on observing the object. So that's going to be clearer after, I guess, when I present the model, what the difference with the benchmark case is. And finally, what happens if you have a centralized model rather than decentralized model. Okay. And here are the main results, as I said. I mean, the first main result is that the game will admit a unique Nash equilibrium. Every node will be attacked through a single path. And I'm going to show you how you can characterize the attack paths through a simple recursive algorithm. You can also compute attack probabilities as a solution to a system of quadratic equations. And the comparative statics properties, the surprising one is that the attacker may be harmed by the addition of new edges. And that's going to be somewhat related to what's known as Brass's paradox in transportation economics. So let me remind you that Brass's paradox is the idea that if you have a road network, if you open a new road, you may actually increase the congestion in the network. And it's a little bit the same thing happening here. By adding a new link, you may actually increase what is the equivalent of congestion here, which is defense, in such a way that it's going to harm the attacker. And for the regions which are closed, the attacker could actually be worse off if the targets increase. So give me 1 second. I'm going to bring in the 3 spectators and allow them to enter. Okay. Sorry. So one last slide for the introduction, and then I move to the game. Just to, I mean, this, maybe I shouldn't spend too much time, but this related to the literature on network interdiction, as I said, in OR. And as you see, this is not a recent literature. I mean, dates back from the 1960s. It's also related to the more recent literature of attack and defense in networks, mostly Sanjeev Goyal and Marcin Dziubiński, and we have a recent paper with Bhaskar Datta and Dziubiński also on attack and network and defense in networks. Basically, in that research program, what the difference between those different papers is that each and every time we look at a different version of a game. So that version of attack and interception, for example, is something that people that had not been looked at before. So I won't say more. I will just let you read those papers if you're interested. So let me pause for a minute and see if I'm happy to enter the game otherwise. Okay. So the game. The attacker is located at some node, 0, Baghdad in my example, and he's connected to all the other nodes through an undirected network. Each node has a value BI, and nodes will have different values. So BI is different from BJ for all IJ. That actually turns out to be super important for our results, but view it as a genericity assumption. Basically, it says that if that were not the case, then you could change a little bit, perturb a little bit the value of a target, and that would give you that result. So we only need an epsilon difference between the targets to get our results. Defenders have access to an interception technology. An interception technology in the benchmark case means I invest in a security portico at the airport, which will allow me to screen all the passengers going through the airport. And one way, and you can choose actually the level at which you're going to be investing in security. And XI, what you're choosing is basically the probability of interception. So, and the cost is going to be half of XI squared. So we look at the quadratic cost, and everything will be normalized in such a way that the marginal cost at 1 is always going to be larger than the values of the nodes. So we take the values to be smaller than 1, all the BIs to be smaller than 1. That guarantees that the marginal cost is 0 at 0, higher than the value of the node at 1. So nobody will want to invest more. I mean, we'll get an interior investment in XI. So the attacker will choose a target, and he will also choose a path to attack the target. So I not only choose to go to I also tell you which is the path that I'm going to be using to go from 0 to I. So a strategy for the attacker is going to be a path and a target. So a mixed strategy is going to be a probability distribution over all possible targets and all possible paths going from 0 to that target. Defenders are going to be choosing what in the end is going to be a pure strategy. It's basically the amount, the XI, the probability of interception. And then we look at what happens. So if the target is hit by the attacker will obtain the value BI, and the defender is going to suffer a cost minus BI. Now, one thing which is important here is that there is no externalities among defenders. So if London is attacked, Paris and New York are not going to be suffering any negative payoff. That's important for our story here. Whether or not it's true is of course, I mean, depends on the applications, but here we're viewing each and every node as being completely self-centered and uninterested in what's happening in the other nodes. notice what we put in red here is that this is not a zero-sum game, and it's not a zero-sum game because we have those interception costs. So it's not that you only get BI and minus BI. The defender also has to pay the cost. And that makes it a non-zero-sum game. And what that means is that actually we're not going to be able to compute values as you would do it in a zero-sum game. So let me start with two preliminary results, which are super important and basically allow us to make the model much simpler. The first result, the first lemma here really comes from the fact that if you are an attacker and you attack different targets, you have to be indifferent among the different targets, which of course makes sense in a mixed strategy. And the first expression here, the expression under 1, basically looks at what happens if you attack two successive nodes, two successive targets, I and j. And what it says is that the value of target j has to be equal to the value of target I times the probability that the object is not intercepted at node I. And when you think about it, it's very clear why that should be the case. It's because the attacker has to be indifferent between going from j to I. What is his expected payoff of going to j? Well, it's the probability of reaching j, not being intercepted at j, times bj. What is his expected payoff if he goes to I through j? Well, it's the probability of reaching j, not being intercepted at j, and then going to I and not being intercepted at I times the value of the node at I, which is bi times 1 minus xi, times the probability of reaching j. So the probability of reaching j appears on both sides of the inequality, so we can get rid of it. And the only thing we have is bj on the right-hand side and bi times 1 minus xi on the left-hand side. Okay, so if you attack two successive targets, that has to be true. If you attack two targets which are not successive targets, but they're two what we call first targets, so targets which have no other target between 0 and themselves, then you have to be indifferent between the two, meaning that bi times 1 minus xi, which is the probability of attacking I and being successful at I, has to be equal to the probability bj times 1 minus xj, which is the value of j times the probability, times the fact that probability of not being intercepted at j. So those are going to just be expressions of the fact that that the attacker is indifferent between different nodes in his support, but they are going to give us extremely strong, they're going to have very strong consequences. The first consequence it has is the following. Look at equation 1 here, and suppose that node I is attacked from two different paths, P and P prime. Well, then there must be that two nodes, J and K, which are preceding nodes on the path P and on the path P prime. But then that expression says, because Xi is the same, because the investment that you make is not done at the level of the edges, but at the level of the nodes, it means that Xi, you're defending your airport, you're not defending the air links. So Xi is going to be the same whether you attack I from J or from K, which means that if you attack I from J and from K, it must be that Bi times 1 minus Xi is equal to Bj, and Bi times 1 minus Xi must be equal to Bk. But that contradicts our assumption that Bj is different from Bk, so it's impossible. And that immediately tells us that it cannot be that you attack the same node I through two different paths, which is a huge simplification, because now it tells us that we don't need to keep track of we don't need to look separately at the fact that you're attacking I from P and P prime. So from the attacker's viewpoint, the only thing which matters is the probability distribution over targets and not the probability distribution over targets and paths. Okay, so we can forget about the paths and just look at the probability distribution over targets. Any target will be attacked through a single path. We still need to characterize the path which is going to be used between Baghdad and New York. We don't know whether you're going to be going through Dubai, from Beirut, London, etc. And I'm going to show you exactly how you do it. But we know that actually you're only going to be attacking New York through a single path. You're not going to be attacking New York both through Istanbul and through Beirut and London. Okay? So some notations here, very simple notations. Alpha I is, if you look, is the probability of reaching I, but without taking into account the interception at I itself. And I'm going to call beta I the probability of reaching I and not being stopped at I. And that allows me to compute the payoffs. So it took me a while before, it's not immediate to compute the payoffs of that game, but this is the payoffs. These are the payoffs. 0 is the attacker. X1, Xn basically tells you this is the defense expenses, the defense expenditures at each and every of the targets. Q is the probability distribution over targets. And the expected utility is the sum over all targets of beta I, which is the probability that you reach target I and you're not stopped at I, times Qi, that's the probability that you're attacking I, times Bi, which is the value of target I. What is the expected utility of the defender? The defender at I has an expected utility, which is minus beta I Qi Bi, minus 6i squared divided by 2. But I decompose beta I into alpha I times 1 minus 6i. Okay, so remember, alpha I is the probability of reaching I. Beta I is the probability of reaching I and not being stopped at I. So minus alpha I times 1 minus 6i. I write it like this because then it becomes clear what the optimal strategy of the defender should be. It just chooses xi to maximize this expression here, which gives us the value of xi, which is just alpha I times Qi times Bi. Okay, so the defender's strategies are not interesting here. All the action, all the meat is in the strategy of the attacker and in understanding what is the attacker going to do. Okay, are there any questions about the payoffs? Okay, so an interesting part is existence of equilibrium. Game of attack and interception always admits a Nash equilibrium. Possibly in mixed strategies for the attacker, it's always going to be in pure strategies for the defenders. The first meaningful proposition is this one. It basically tells you when is it going to be that the equilibrium is in pure strategies. Well, for an equilibrium to be in pure strategies, what you need is that one of the targets has to have a much higher value than all the other targets. And when you think about it, it's very intuitive that to have an equilibrium in pure strategies here, meaning that the attacker is always going to choose the same target no matter what, you need that target to have a very high value because all the other targets are going to choose a defense of 0. They know that they're not going to be attacked, so they should not spend any money in defense. The only node which is going to choose defense is the node which is attacked in the pure strategy equilibrium. And that node is attacked with probability 1. So remember, xi is equal to alpha I times bi times qi. Qi is equal to 1. The node is going to be attacked with probability 1. Alpha I is going to be equal to 1 because you don't attack any of the previous nodes. The previous nodes are not going to put any defense, so you're just going to send the bomb without any difficulty through those different nodes. So alpha I is 1, Qi is 1, so xi is going to be equal to bi. The amount of defense that you choose is bi, so the probability that you reach that node is going to be 1 minus bi. That you reach it and successful is 1 minus bi. So from the point of view of the attacker, the expected utility is going to be bi times 1 minus bi, which is what you read here. Okay, so for that, so remember bi is a number between 0 and 1. So bi times 1 minus bi is going to be a number between 0 and 1/2. And what you need is that that number be greater than all the values of all the nodes which precede I if there's a path between 0 and I which goes through J. Why is that? Because if that were not the case, then the attacker would have an incentive to attack node J, because node J is not defended, so he gets Bj if he attacks node J. And if Bj is greater than Bi times 1 minus Bi, that cannot be an equilibrium. The second condition basically says that if you look at all those nodes which are not located on a path between 0 and I, so possibly nodes which are located after I or on different paths, well, it must be that Bi is greater than or equal to Bj for those nodes, because if that were not the case, then the attacker could actually choose to go to skip I and go to J instead. Okay, and by skipping I and going to J instead, he would be successful with priority 1 minus Bi and get Bj times 1 minus Bi. Okay. So what that means is that it's very unlikely that you will have a pure strategy equilibrium here. It will only happen if one of the nodes, if one of the targets in the network has an extremely high value. Most of the simulations that we run did not have that property. So that was a situation where you had a mixed strategy equilibrium. So the next question is basically now to characterize a mixed strategy equilibrium. So the first lemma here is a lemma which is going to tell us how do you attack. It's going to tell us something about the values of the targets which are attacked one after the other. So let's read that lemma. It says, suppose that I is attacked. I is in the support, I is in attack. Then it says that any node J, which is a preceding node, P of I means that it's a node which is preceding I on the attack path between 0 and I, all those nodes must have a value Bj which is smaller than Bi. Okay, so all the nodes, you basically attack nodes in an increasing sequence. Nodes which are closer to the attacker will have a lower value. Nodes which are further away from the attacker on the attack path will have a higher value. The second point says you will continue to attack nodes as long as those nodes have an increasing value. So suppose that I is the node that you attack, and that there is another node J, and there's a path going from I to J, and nobody is attacked between I and J. Then it says that if J has a higher value than I, you must also attack J. So you will be attacking nodes which have a higher value. So think of a line, for example. If the network that you look at is a line, what that lemma says is that there's going to be one node, which is going to be the first node attacked. And then I know exactly which nodes are going to be in the support. All the nodes which belong to a sequence of increasing value are going to be attacked. So I look at the first node following the first node, which has a higher value, it's going to be attacked. Then I look at the first node following that node, which has a higher value than that node, and it's going to be attacked. So basically, I'm constructing that sequence of nodes of increasing value, starting from node 1, and this tells me exactly which are the nodes which are going to be attacked. Okay, so I'm going to give you examples which are probably going to make that clearer. Now, the second lemma on this slide basically tells you exactly how I can identify the path of attack to one particular node. It says, suppose that your node I is a node which is attacked and it belongs to delta M. That's a notation to say that actually it's not a first target. So it's a node which is not attacked as a first target. There are other targets which are attacked before it. And it says, well, which of those targets am I going to attack I through? And it says that actually you will always choose the target with the lowest value. So if you can attack I through different targets, you will always choose a target which is the target with the lowest value. And that is actually a way to construct recursively. If you give me the support, that means that you can recursively construct the attack paths by looking at the nodes which are the further away from node 0 in the support. Sorry. And this is going to be the way that I'm going to be able to construct the equilibrium attack paths. So this is the way that, this is how I use this. First, I'm assuming that actually each of those cities are going to be part of the support, are going to be attacked with a positive probability, which actually, given the numbers that I gave you, is going to be true. Then I look at cities like London. London, there was no direct flight from Baghdad to London. So London is not a first target. Then I need to look at those cities, Amman and Beirut, which were first targets that you can use from Baghdad to London. And I realized that the one with the lowest value is Amman. And because it's the one with the lowest value, I know that London is going to be attacked through Amman. Because there were no direct flights between Amman and Paris, Paris cannot be attacked through Amman. Paris is going to be attacked through Beirut, because Beirut was the city which was the lowest value among the cities which have a direct connection to Paris. Now let's look at New York. New York had a connection to London, Paris, Istanbul, and Dubai. By the same reasoning, New York is going to be attacked through the city which has the lowest value. And that's for Rami, the city with the lowest value is Istanbul. So New York is going to be attacked on Turkish Airlines from Istanbul to New York. Okay. So that's the first part of the story. It's basically the way that we can construct those attack paths that the terrorist is going to be choosing. Second part of the story, what is going to be the probability that he's going to be attacking each and every of those cities? And that, again, we can characterize. So we characterize differently actually in delta 0 and outside delta 0. So delta 0 are first targets and outside delta 0 are not first targets. So let me tell you where this comes from. Xi is equal to 1 minus bk divided by bi. This is exactly lemma 1, because it says that bi times 1 minus xi is equal to bk, where bk is the predecessor of I. So it just comes from the fact that the attacker, when he attacks successive targets, must be indifferent between the successive targets. And that gives you equations 4 and 6. It's basically equations which tell you that the attacker is indifferent among the targets in the support. Equations 5 and 7 come from, it's a rewriting of the optimal choice of the defenders. And it's a rewriting in such a way that it isolates Qi, where Qi is the probability. So if you look at this in the end, you have U, which is an auxiliary variable which measures the equilibrium utility of the attacker. But from 4 to 7, this is a system of quadratic equations. Okay. It's actually, sorry, it's not quadratic equations. Let me take that back. It's a system of equations, which is just a system of equations. If you give me a value of U, I can compute the values of xi and qi directly here. So, and then the 8th equation is a way to compute the value of U. It tells us that the sum of probabilities has to be equal to 1, and that's going to be the way to compute the value of U. So U is going to be the fixed point of, when you replace all the Qi's here, you get an expression which is going to be the fixed point of an equation in U. So that gives you an equation in U, and it turns out that that equation is strictly decreasing in U, so it will have a unique solution. So what that says is that the system of equation has a unique solution. This, for example, with the numbers that I gave you, this is the solution that you get. Amman is going to be attacked with probability 2.88%, Beirut 5.47. You can read it. New York City with a probability almost 30%. Okay, so this is the characterization of equilibrium. Once I get the support, so all this was done assuming that all the cities are attacked in the support. If you give me the support delta, I can compute the equilibrium attack paths using the fact that you're always attacked through the point, through the target which has the lowest value, and then I can compute the equilibrium attack probability solving that system of equations. The difficulty is going to be to identify what the support is. And that's where the difficulty, the technical difficulty of the paper is. It's going to be to show that actually the support delta is unique. Okay, so once the support is given, the equilibrium attack paths are uniquely determined. The difficulty is to show that you cannot have two different equilibria with different supports. So I'll tell you very briefly the ingredients of the proof. The first part is to show that if you had two equilibria with different supports, it would mean that actually one node is attacked in the equilibrium E, but not in the equilibrium E prime. Well, that will actually imply that the expected utility of the attacker has to be higher in the equilibrium E prime than in the equilibrium E. Otherwise, you can show that there's a contradiction. He would actually be attacking that node which is not attacked. So, and in fact, that goes even further. It shows that if the supports are different, actually one of them must be included in the other, and that's also linked to the fact that the expected utility of the attacker must be strictly higher in delta prime here than in delta. So it means that he attacks fewer nodes in delta prime than in delta because he gets a higher expected utility. We also show that the equilibrium attack paths have to be the same. In other words, think about attacking a node in delta prime, then you go through the nodes, and those nodes have to be the same as the nodes that you would be choosing if you were to attack it in E. The next step of the proof will be to show that actually the equilibrium attack probability under delta prime is smaller than or equal to the equilibrium attack probability under E. And the final contradiction is obtained because we know that the sum of probabilities has to be equal to 1. We've shown that actually the equilibrium attack probabilities under E prime are always smaller than or equal. And we also know that the number of points which have positive probability is strictly smaller. So it means that sum of Q prime has to be strictly smaller than sum of Q, which is the desired contradiction. So it's not an obvious, it's definitely not an obvious or a trivial result. It comes both from looking at the fact that the attacker is indifferent across the different points in the support, and also it uses very strongly the graph theoretic notions, the fact that actually you have paths and you can only attack I through J, and that gives us a condition between Bi and Bj. Okay, so I don't think this is something which, it doesn't come from a very simple result that we can apply off the shelf. I think it's really tailored to the particular model that we look at. Okay, and let me conclude on the equilibrium characterization by telling you that it's usually very hard to compute the support delta. So I could do it, for example, in the Baghdad to New York and London and Paris, because this is a simple problem with a small number of nodes. But if you gave me a general graph with a large number of nodes, I don't know of any good algorithm to compute the equilibrium support. I know one when the graph G is a tree, but even then it's not easy. So here is one case where it's easy. It's when you have a line. When you have a line, you only need to identify what is the first node which is going to be attacked. Because after that, you just construct that sequence of nodes with increasing value that I was talking about. And you know that all those nodes are going to be attacked one after the other. So that will give you the support. So you only need to identify the first node in the support. And this is the way that you identify it. And you, as you see, this is not at all obvious. Okay, it's a complicated expression of the BIs and BJs. So construct B1 to Bn to be an increasing sequence of targets along the line, starting with the first node 1. And you pick that first target for which this is going to be the case. You can show that there's always going to be a target for which this is going to be the case. And then this is going to be the first point, and all the following targets with higher value are going to be attacked. Okay. Let me stop here for a minute. I also need to ask you, Rami, how much time I have before.
Let's say 15 minutes more or 15, 20
Very
minutes.
good. Very good. Okay, so we know how the terrorist is going to attack our particular network. Let me quite quickly go to the comparative statics, because then I want to tell you a little bit about the two variations of the game. So the first thing we do in the comparative statics is that we're going to look at what happens if you add an edge to the network. So you add, suppose that you have a new airline, which basically creates a new relation between two cities. So this was the initial situation. You had the attacker 0, 3 targets, 1, 2, and 3. The values of the target are given by what you have here, 0.275, 0.3, 0.4. You can compute the equilibrium attack probabilities is you're going to attack 1 with priority 2%, 2 with priority 29%, and 3 with priority 69%. Now, let us imagine that a new airline creates a link between 0 and 3. Now, the point of that example is to show that by creating the new link between 0 and 3, by creating the new link, you can now, you're basically going to 1 is not going to be attacked with any probability anymore. 2 is going to be attacked with priority 24% and 3 with priority 76%. So in other words, creating a new link changes the support here. Okay. So we have to be careful when we look at addition of an edge, because it may change completely the support of equilibrium. So what I do now is basically I'm saying, suppose that I consider adding an edge, but keeping the support intact. So this is actually it's a complicated proposition. There's a lot in it. So I don't know if it's a bit scary. So I'll just tell you a little bit what's going on here. So what you do is you have two nodes I and j, and you add the link between j and I when there was no link before. So j was in the support and j was attacked through another node k. So you now make it easier for the attacker to attack j, because now there's a direct route from I to j, whereas before j was attacked through a complicated route going through k. Okay. And the question is, how is that going to change the equilibrium utility, the equilibrium probabilities? And this is what we're saying here. Now, the first thing we know is that actually the defense of node j, which is now closer to the attacker, is going to go up. We also know that all the other nodes are not going to be affected, except possibly nodes which are first targets. Now, what's interesting is that depending on whether bi plus bk is greater than bj, so remember bk is the value of the node which was the predecessor of k before, j before, okay? And if bi plus bk is bigger than bj, or bi plus bk is smaller than bj, we know that both bi and bk are smaller than bj, but the sum of the two could either be higher or smaller. So the two possibilities exist. And according to that, in one case, the expected utility of the attacker will go up, but in the other case, the expected utility of the attacker is going to go down, which means that adding an edge to the network could in fact possibly hurt the terrorist. So the terrorist could be worse off if there's a new airline which starts a new link, which actually makes some cities closer for the terrorist. So that initially came to us as a surprise. We view that as a paradox, because initially we thought, well, the terrorist can always forget about that new link and do what he was doing before, which was just use the attack paths that he was choosing before and completely ignore the new link. But the problem is that this is not going to be an equilibrium, because he will be willing to use the new link. And so he will have to use the new link. And by using the new link, he kind of commits to using the new link. And that is actually going to create to change the way the defense is going to happen. It's going to increase the defense, and that in the end is going to make him worse off. And this is almost exactly what's happening in what I call in the Brassus paradox. In Brassus paradox, the fact that you create a new road is going to change the way that agents are going to use the network, possibly, and could create more congestion. So it's the same kind of paradoxical effect through the kind of feedback loop here due to the fact that you have defense, and defense is actually going to increase. So we view that as a surprise, actually. I'm going to skip the other comparative static, which is a comparative static in changes in target values. I'll let you read it. And instead, I want to talk about two different versions of the model. The first variation of the model is basically to say, well, so far we've assumed that what the defender does is basically choose ex ante how much he's going to be inspecting. But there may also be elements which are more variable elements, which are that you can increase your inspection at some times and not at other times. For example, when you know that if you have a tip and you know that a suspicious package is going to go through the airport, maybe you're going to hire new security agents at that moment or bring the police to that particular part and increase the police inspection at that moment. And that creates a different game, because now it's a game where you choose how much to inspect, not ex ante, but upon observing that there's a suspicious package going through you. And now this is not going to be a simultaneous game anymore. It's going to be an extensive form game. And we're going to be using sequential equilibrium as the solution concept and not Nash equilibrium. So let me show you what I have in mind. Suppose that you have a network with three potential targets like here. 0 can, and the attacker can attack either 1, 2, or 3. Well, this is the extensive form game that I want to look at. If 0 attacks 1, it means that the suspicious package is going to arrive at 1. And 1 then decides how much to choose in inspecting. If 0 attacks either 2 or 3, the suspicious package is going to go through 2. When 2 receives the package, 2 does not know whether the package is going to explode in 2 or in 3. So 2 cannot identify whether he's in that information. That's the information set. He doesn't know if he's at that node or at that node. And he will have to choose an inspection strategy x2, not knowing whether he's here or there. When 3 receives the package, 3 has to choose the inspection. Here, actually, when 3 receives the package, 3 knows for sure that the package is going to be targeted at 3 because there's no other possibility. So the last node knows for sure that that he's the target. Okay? So that's the game to look at. It's a complicated game because it's a game where people will have to have beliefs about whether or not they are going to be the final target of the bomb. So for example, if the bomb goes to 1, if the strategy of the attacker is to attack 1, and 2 receives a suspicious package, this is off equilibrium. So 2 needs to form off equilibrium beliefs to know what he should think when he receives a package here. Okay, so it's a completely different world. And what's strange or interesting here is that we get the exact opposite results to the ones that we get in the simultaneous game. The first result we get is that actually the only equilibria are going to be pure strategy equilibria here. Okay, so make an assumption here, which is another genericity assumption, and assume that this assumption holds, that the underlying network G is a tree. Then in any sequential equilibrium, the attacker must attack a single target with priority 1. I'll give you the intuition. If you are, suppose that you have a mixed strategy equilibrium, and I'm the last target on one particular path. If I'm the last target on that particular path, I will know for sure that if I'm attacked, if I receive a package, I know for sure that I'm the destination of the package. So the probability of me being the target is going to be 1. And so I'm going to be defending with probability xi is equal to bi. So the defense is going to be bi times 1 minus bi. The defense at the last target is completely pinned down. It's bi times 1 minus bi, irrespective of what the probability distribution of the attack is going to be, because if the package arrives at that node, it means that I'm the target. Well, if that's the case, it means that I'm attacked with probability, I get bi times 1 minus bi as the attacker. But then think about the previous node on the attack path, node J. That node, when he's attacked, will be attacked and get bj. So it means that for the attacker to be indifferent between the two, it must be that bi times 1 minus bi is equal to bj. However, we're assuming here by genericity that bi times 1 minus bi is not equal to bj. And what that means is that that's an impossibility. So you have to attack using a pure strategy. So it's the complete opposite to the simultaneous game. Another opposite to the simultaneous game is that actually in that case, you can have multiple equilibria. It could actually be, you could construct one sequential equilibrium where you attack one node with priority 1 and another sequential equilibrium where you attack another node with priority 1. So we do it on the line because it's easy to do on the line. We can actually identify on the line exactly those targets which can be attacked in one sequential equilibrium. So that's the condition here. It says that target I must satisfy bi times 1 minus bi greater than or equal to bj for all j smaller than I. So remember that was one of the conditions actually for pure strategy equilibrium in the other game. But we have another condition which is actually weaker than the condition that we had in the other case, which is that bi has to be greater than or equal to this probability. And if you look at a line with 3 nodes with values 1/5, 2/9, and 1/2, you can check that both node 1 and node 3 satisfy those conditions. So you can construct an equilibrium where node 1 is attacked, and you can construct an equilibrium where node 3 is attacked. So the reason why you construct an equilibrium where node 1 is attacked is basically because we construct beliefs in such a way that 2, if he receives the package after node 1, believes with priority 1 that he's going to be the target, so puts a lot of defense, and 3 puts a lot of defense as well. And so because 2 and 3 put a lot of defense, it's not in the interest of one of the attacker to try to attack 2 and 3. Alternatively, you can construct an equilibrium where you only attack 3, and nodes 1 and 2 then are not going to be putting any defense because they know that they're never going to be attacked. But because b3 times 1 minus b3 is greater than or equal to b1 and b2, then that's going to be satisfied here. Okay, so I have very little time and I'm afraid that actually I'm going too fast. But let me just mention that in that sequential version where you only inspect upon observing a suspicious package, we get almost the opposite results to the ones that we got in the simultaneous game. We get pure strategy equilibria and we get multiplicity of equilibria, whereas before we got mixed strategy equilibria and uniqueness of equilibria. I have 2 minutes left, and that's going to be enough to tell you one word about what you get when the nodes cooperate in defense. So that is really what most of the literature has looked at. What if you have a single defender which chooses the defense levels on the different nodes? If you think about airports, what I mean is basically suppose that you can actually subsidize the airports in Beirut, Istanbul, or Dubai. You're the US, but you can actually send security people in Beirut, Istanbul, and Dubai to beef up the security. That's what we have in mind here. Now, this is a completely different world because now you may want to protect nodes even if they're not attacked. Even nodes with very low value, which are not attacked, if they are located on the path going to you, you may want actually to defend them. And that creates actually much more complicated defense strategies. And I don't have the time to go through any of that. So I'll just skip to one proposition, which is the following, which is a comparison between a model with and without cooperation, and we could only do it on a line. So suppose that you have a line with n nodes of increasing value. What we're writing here is that if you compare cooperated defense with non-cooperative defense, you realize first that the attacker is always worse off when the defenders cooperate, which is not surprising. As a whole, all the defenders are better off cooperating than non-cooperating. But if you look at each defender individually, you realize that all those which are not the first targets, so 2, 3, up to n-1, get the same value, get a higher value, if they cooperate than if they don't cooperate. The last node gets the same value under cooperation and without cooperation. And the only one for which we don't know is the first target. So the first target, the first node on the line, it could, depending on the values, get a higher or lower value when the nodes cooperate or when they don't cooperate. So the message is that you may actually need to subsidize, but you will only need to subsidize the node which is closest to the attacker. So it's only Istanbul, Dubai, Beirut, and Amman that you may want to subsidize. You don't need to subsidize intermediate nodes. Okay. So let me finish here. So this is a long list of the results that we have, so it's a little bit boring. Let me just summarize it by saying that what we have is a game played in a network where you have an attacker and you have possible interception. We were able to characterize the equilibrium of that game and show that it has a unique equilibrium in mixed strategies. We were able to do some comparative statics and to study some variations. Now, the next step, we believe, would actually be to try and see if you were the airport, what would you like to do? What kind of map of air flights would you like to construct in order to make it as hard as possible for the attacker to attack you? So it's a little bit going back to the network interdiction question. If you could design the network, if you could choose the network, what would be the optimal way of choosing the network if you want to prevent attacks? Okay, and let me stop here.
Okay, any questions? No? Okay, thanks a lot, Francis. I thought nothing interesting could be said about network attack, since the literature is so old, but definitely it can be said apparently. So thanks a lot for this very interesting talk.
No, thanks a lot. And again, I mean, I just imagine that I'm in your beautiful new building at the university, and I hope to see it very soon. Huh?
Hopefully, definitely.
When we're all vaccinated.
Definitely, hopefully. Okay, thanks again, Francis.
Okay, thanks a lot for the invitation.
Thank you. Very nice talk.
Thank you. Okay, thanks for all the participants, and bye-bye.